All right, this is our first lecture for statistics, and I'm just going to go over some points in section 1.1, and it's really going to be about ideas. It's not going to be really any computations. We'll talk a little bit about percentages, but it's really about what is statistics. What is it we're doing? And it's not necessarily the same kind of thinking that you were used to in algebra, where we have formulas that establish a relationship between something and something else, that there's a cause and there's a clear effect. We're going to be talking about something a little different than that. And we're going to get situations where we could have consistent change, where this changes and this also changes. This changes and then this changes. But that doesn't mean there's a relationship, and that's sort of sometimes a difficult idea to grasp when you're first learning statistics. You might have which is simply a coincidence, but we'll see this in the mathematics. The mathematics will still say there's a strong correlation between the two. It doesn't mean we can conclude that they're actually affecting each other. So this is a part of statistics that can get a little tricky to understand, even to accept. So we're going to dive into it and get into a little bit of what statistics is. Why is it going to be different compared to, say, other mathematical studies? All right. So first off, we're going to talk about statistical thinking. And the textbook basically divides this into two areas. The first one is called critical thinking. Now, critical thinking itself, you'll find some definitions that vary on this one. So I'm going to give you 3 sources I found online that will give some idea of what critical thinking could be. The first one's from, of course, our favorite standby, Wikipedia. And according to Wikipedia, critical thinking is using facts to form a judgment. Now, what could be tricky about this is facts. When we're talking about statistics, specifically statistical studies, the reason we're doing the study is we don't have the facts. So we're trying to hone in on some kind of fact. And we might not have enough to back us up to make a strong judgment. We might say, really, that when this changes, this changes. And they just happen to change with each other. It doesn't mean one's causing the other to. So we want to be careful about this. We may not have all the facts that we want. We're actually trying to zero in on some kind of a fact, but the judgment we make about that fact, say the fact is that we observe this apparently change at the same time, do we say that one affects the other? And the answer could be we don't know that much. Say if we're looking at how a drug, if you take some kind of a medicine in a study, is this going to, cure some virus or remove some virus from your body? Well, we need to be careful about determining if this is actually affecting it. We could have some kind of unusual coincidence going on. When we do the study. Maybe we do this study during a certain time of year when, this virus sort of starts to go away. It works its way out. And it happens to be the time of year that we're doing this test for this drug. So as we do this study, we see that, people's viral counts are going down, and the number of people getting sick are going down, and this drug we've been giving is increasing it. We're getting it out there. Maybe this has some preventative properties, we hope. And it's like, golly, it looks like this drug's really preventing people from getting sick. But again, it could also be a time of the year where this virus starts to go away. We don't see it in people. So when we see the number of people getting sick, as we increase the number of people taking this preventative drug, well, that could just be coincidence, and we don't know it. So we have to be careful with our judgment. Ultimately, we want to be able to see, is the drug actually doing something with, well, the molecules of this virus that's breaking it down or something, or it's somehow reinforcing the immune system of the body. We can make those kinds of observations to better say that, oh yeah, this drug is causing people to be immune to this virus. We want to be careful that we don't have some kind of coincidence going on. Again, as the year changes, the seasons change, people just aren't getting sick as much from this kind of virus. And it happens to be the time period that we were administering this drug. And the more people we get, as we increase the drug, people seem to be not getting sick, but it's really because of the time of year, not because of the drug. We've got to be very careful about how we make these judgments about facts or phenomena we see in the universe. And this is sort of at the core of statistics. So critical thinking is, yes, we're going to use facts to form judgments. We just got to be very careful, though. That's going to be a really important thing in this class. All right, so that's Wikipedia, facts to form a judgment. Also important here, too, is that staying away from subjective speculations. That's probably the key thing here. Statistics, of course, we're going to be careful with facts, careful with judgment. We might not have the facts we want, and we can't quite make the judgment we wish we could make. But here they're probably getting at something a little bit different. We're going to try to use facts to make our judgments. We're not going to use speculative or subjective ideas or well, predispositions to make these judgments. We're going to try to go with facts. All right, that's Wikipedia. Let's take a look at Google. All right. So Google is objective analysis and evaluation of an issue to form a judgment. So once again, we're going towards this goal of, can we say something about what we're seeing? That's where we're going. We have some kind of goal. It seems to be, we're going to make some kind of judgment. And we're going to be careful. We want to have facts. We want to be objective. So again, not speculating, not using these sort of subjective inputs. And that's going to be actually hard to do. We're going to talk about issues of bias throughout the class, and it's not as easy as you might think. So we're seeing some consistency here between Wikipedia and Google. All right. Maybe it's just coincidence, though. Well, let's take a look at another source. So the Stanford Encyclopedia of Philosophy. What did this say? Well, take a look. And this is they have some other, they break this down more, but a very sort of quick summary. Careful, goal-directed thinking. Careful, goal-directed thinking. So there's some other points that come into this. For example, I'll mention some of the things that they added to this. The idea of having a goal they mention is to determine what to believe and what not to believe. Again, we're kind of heading in the direction of judgment. Should we believe this or should we not? Another thing they mention is having appropriate and adequate standards. So with critical thinking, there needs to be some kind of standard regarding your performance. And probably a standard people are going to have is you're going to probably be dealing in facts instead of subjective things. If your goal is realistic and involves something in the real world, you're going to want to have, well, material that's from the real world, not just from our imaginations or from our prejudices. So we want to make sure we have adequate standards when we do this careful thinking. And they make an interesting point, the third one. The standards fulfill a relevant threshold. Relevant threshold of what? One thing that comes to mind might be a kind of quality control, and it's relevant. First off, it's significant. Your level of appropriateness, your level of being factual, being objective, it needs to be substantial. But then again, maybe you might worry too much about a bias that's going to be irrelevant. So it might be a relevant threshold. You don't have to be absolutely perfect, but you do want to do everything you can, though reasonably can, to keep biases that will affect the outcome from getting into your work, getting into this careful goal-directed thinking. You don't want to miss your goal and through some kind of, well, just being careless with the facts. So anyway, some insights with critical thinking, and then you've had my opinions on this too. So like the ghost fourth source being me, speculating on some of this too. But the thing that comes out of this is we want to be careful with what we do when we critically think. We want to be careful. We want to try to rely on facts. We want to have some standards in our process of thinking. And it's going to be towards some goal. We're trying to accomplish something with this thinking. And based on the other two sources, it would be to make some kind of judgment. And then from Stanford, it would say, well, we're going to try to determine what to believe and what not to believe. And that's what we're going to try to do. So it looks like we're just being careful, we're being factual to make some kind of judgment about reality. And we're going to have some high standards about how we do that. Anyway, critical thinking. That's one part of statistical thinking. The other part. Making sense of our results. Now, as much, I really like talking about the whole issues of bias and being objective. We're going to find out it's very hard to be objective. That's a fascinating topic. This is going to really dominate also much of our time in the class. How do we make sense of the results? So, okay, we've figured out the right questions to ask. We've figured out the right experiment to conduct. And we've collected our data. We're going to talk about samples later in this class. We use them to represent populations. Population is a group of, say, people or objects that we want to know something about. Could be a group of animals. But we can't actually ask everyone. Let's say we want to know what people's opinions are on, say, I don't know, Subway sandwiches. Well, we can't actually ask everybody in, say, the state of New Mexico what they think of Subway sandwiches. So, that being the case, we can only ask maybe a subset of people. And, well, subset of people, we need to put together a subset, a group that kind of represents the population dynamics of New Mexico. So we do that through this process called a random sample, and we might make some modifications here and there to, try to get a representative sample, and then we'll ask the sample population, what do they think of Subway? Instead of having to ask, how many millions of people there are in the state, we can ask maybe 500 people. And we'll try to draw some conclusions from that. So we've done this, we've accomplished this, we have our results. How do we make sense of them? All right, we have data, we have numbers or yeses and nos. How do we make sense of it? So things that we'll look for. We'll look for patterns. We might compute averages. We might look at the spread of data. We might ask, are the results likely? So these are things we might be interested in. And we're going to use these kinds of tools to help us make the judgments in the very end. So spread of data, for example, we might be seeing that all the values of our data are really close to some number, or we might find they're very diverse, they're very spread out. And so what kind of judgments do we make? So these are some of the things that we're going to use these tools to help us make those decisions, make those judgments on what to believe and what not to believe. All right. So I want to go over some terms. And we're going to have a lot of terms in this class. But these are some basic terms to start out with. So first off, data. What is data? Well, this is a plural word. The book mentions that datum is the singular. If you have one piece of data, you call that a datum. And then data refers to all the numerical information you've collected. Or maybe not numerical. There's data that isn't numerical. So, definition, collection of observations. Statistics. And statistics as a word, you'll see a couple definitions for this. Let me give you the one in the text, or your idea what the one in the text is talking about. It's a science of planning studies and experiments. Planning studies and experiments. Now, in science class, when we do this, we plan an experiment, we don't really think about bias. Now, you might encounter some issues with bias in chemistry. It's why you want to make sure you wash your utensils using deionized water. You don't want to get something else getting into the chemical mix that could throw off your results. Similarly, when we plan studies and experiments and statistics, we want to try to prevent bias from getting into our study or experiment and throwing off the results. And we'll talk about how bias can do that. And oftentimes we're very used to bias being something obvious, where maybe someone is asking a trick question on purpose. We're going to find out bias can be something very subtle and very hard to see. For example, let's say we're going to do a random sample from the state of New Mexico. Population's too big for us to ask every single person what they think about Subway sandwiches. So we're just going to collect, say, 500 people. And we want to try to have a group of 500 that reflects the population of New Mexico. Now, we might say, okay, we're just going to choose 500 people randomly from the state. We have, like, say, phone numbers, phone listings. And so we choose 500 people randomly from the phone listing. And, okay, that might work. Then we might do it a little more careful. We might say, well, we want to make sure that the way we do this random selection, we want to weight it. Because more people live in the Albuquerque area than live in, say, the northwestern corner of the state or the southwestern corner of the state or the very northeastern corner of the state. So we want to make sure that as we sample randomly, we pick people randomly, we want to make sure we're picking more people from the populated regions than from unpopulated regions. Or not unpopulated, but not as populated. So we want to be careful with that. And if we don't take that into account, we might overrepresent under or not as populated places. We might overrepresent them and underrepresent the highly populated places. If you have a random sample of people from New Mexico, you should get most people coming from places like Albuquerque, Santa Fe, Las Cruces. If you just do a uniform random sample, you're going to get as many people coming from, say, northwest part of the state versus, say, people living in Albuquerque, and that might misrepresent the population. So you want to make sure that this is balanced in that way. So that would be a form of bias. It could slip in depending on how you randomly pick people. Again, if you had some computer that says, I'm always going to pick a person here, person here, person here, person here, person here, then here, 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 say there's a map of New Mexico, then you have about the same number of people from, again, one part of the state, same number from another part, same number from another part, same number, same number. That would not accurately reflect the state's population at all. Again, most people in New Mexico are kind of living along that I-25 corridor. So you're going to pick most people in the middle and then proportionally, appropriately, numbers of people who are on the outside of that corridor. Not taking that into account will bring in a form of bias. So bias isn't just like the trick question. It's also how we set up a problem. And just like in chemistry class where you want to clean off those tools to make sure they're clean before you start using them, we want to be careful how we prepare for these studies and these experiments, and hence the importance of planning, science of planning. We want to be careful that we don't introduce these forms of bias without realizing it. Anyway. All right. So this is going to involve getting data, organizing, summarizing, presenting, analyzing, interpreting, and again, this is your data. So organizing your data, summarizing it. Again, summarizing could, again, like what's the average of the data, how spread out is the data, what's the median of the data, what's the mode of the data, what's the standard deviation. Standard deviation is a measure of how spread out it is. So that's one way of summarizing it. Presenting it, we could be using graphs. Graphs are really great at this, graphing our data, using bar graphs, maybe pie graphs. We might look at distributions. We don't just plot the data, just see where the data is located in some kind of a, well, we'll put some axes where we have like, excuse me, an x-axis, a y-axis, and then our data might fit somewhere on that graph. Interpreting the data, what can we draw from this? And in one interpretation we might want to keep an eye out for is what's called the outlier. The outlier is going to be, say, a point that's way outside, like the data's, say, between 5 and 10. Maybe we're measuring the degrees on the mountaintops or something, how cold it is, and it's 5 to 10 degrees Fahrenheit. And then we have this one data point from a mountain of the same height in the same area, and it says it's 100 degrees Fahrenheit during the winter time. And it's like, wow, how did that happen? So we might have to try to interpret what's going on with that one point. We would call that an outlier. So if we're looking at those mountaintops, typically 5 to 10 degrees Fahrenheit during the day in the winter. And then someone said, yeah, the mountaintop, the gauge said, the thermometer was saying that it was 100 degrees Fahrenheit in the winter. And it's one of the mountains that's amongst all these other ones. that might be an outlier. We'll have to try to figure out why is that data point so far off or far off along the number line. And who knows, maybe there's something going on there. Analyzing the data, of course, again, you're going to be using some mathematical methods of doing this. We like averages and things like that. So, well, that's things that you can do. One more point here. And again, drawing conclusions. This is also part of statistics. And we'll find that this can be a very tricky thing to do. Again, we might be dealing with coincidences. We might want to be careful if we say something statistically insignificant. It might mean that there is some practical significance, though, or we could say something's statistically significant. We'll talk about what that means later. But it's not practically significant. Like, yeah, okay, the statistics tell us something's changed, but for all intents and purposes, it's not a significant change, though. It's really not going to help us what we're trying to do or what we were looking for. So we have to be careful how we draw conclusions. All right. So the process, let's see here. We're still looking at terms. Population. So this is the complete set of all data that we want. So you can think of it like this. You sort of transform yourself into a number. Someone wants to do a statistical study again. Well, how would you rate Subway sandwiches from 1 to 10? And let's say it's one particular sandwich. And so you want to ideally ask everyone in the state of New Mexico, okay, you just become that number. Is it a 1? Is it a 5? Is it a 10? Something. And all we got to do is find that number, is what we're doing. So we all have this data in us that some statistical researcher wants to know about. There's going to be a problem here, though, as that data is not necessarily available. Now, it's not because we're being stubborn. It could be that, well, they don't know how to get a hold of us. Like, I'm giving this lecture right now. For all that I know, there's some statistical researcher calling me up saying, oh, I got to get some answer and I got to ask you some question. It could be about my thoughts on taxes or something, or Subway sandwiches. But I'm here. I'm not next to my phone. So that means they won't get the answer to that question. So there you go. The data is out there, possibly, but well, it's not available. It could also be it's too expensive to actually go to every single person and get the answers. It could take forever. So, and it could cost a lot of money. So it might not be possible for those kinds of reasons too. The ideal that we're looking for is a census. This is related to population. And this is a collection of the data from everyone in the population. Collection of data from everyone in the population. And again, for very practical reasons, this might not be possible to put together. So what do we do? Well, we do this. We're going to settle for a sample. And this is going to abbreviate as population, a sample of the population. And this is basically a subset. And the idea, and this is going to be something that's going to be important, we want to have this subset be incredibly similar in various characteristics to the overall population. And so even though we can't study the entire population, usually not, we could at least study the subset. If the subset, think of it as like a scaled down version of the population, and if the sample represents the population well enough, at least for the study that we're trying to conduct, then the questions we ask of the sample, it will be like asking the same questions of the entire population. So that's a big goal here. Coming up with a sample is going to let us do our study. All right. So we're going to look at the process of a statistical study. All right. First thing we're going to do, I'm going to prepare. So what do we need to do first? Well, first off is we want to identify the context. So what does that mean? What's the context of the study? Well, first off, is the research goal is it reasonable? So the question regarding Subway sandwiches, can we come up with a sample that's representative of the population of New Mexico? Or hopefully it'll be accurate enough that we can draw a correct conclusion from it. Well, we'll do our best. Then can we take the sample once we've assembled, say, 500 people together? Then can we ask them the question? Well, yeah, of course we can do that. So there we go. Okay, that seems like a reasonable goal. But if we have a goal like we want to find out if people tend to prefer more ketchup on hot dogs when they're on Mars or mustard on hot dogs when they're on Mars. Now at this time, no one's been to Mars yet, though we seem to be getting pretty close to that. There's some problems with this that are practical. First off, of course, we don't have anyone who's been to Mars. And even in the next, say, 10 years or so, we have people landing on Mars and coming back or staying there for some time. That's going to be a pretty small sample of the entire human race. So, and it might not be a very representative sample. I mean, these are astronauts. These are hardworking people, and maybe they hot dogs give you sort of afternoon food coma. And they're like, I can't get food coma. I got to do some training for the next launch to the space station. So maybe they don't get hot dogs all that much. Who knows? There's all kinds of things that could go into this. So that research goal about the hot dogs, ketchup, mustard, people on Mars, that might not be very reasonable for trying to understand what the entire human race would think of ketchup versus mustard if they were on Mars. Now, we might be able to do a study of astronauts or people who've been to Mars. And, well, not at the moment, though, because no one's been there, and there haven't been, even in the next few years, if we start landing on Mars, well, not a whole lot will have gone of the entire astronaut corps. So again, it might not be a very reasonable goal to pursue. So, okay, something to think about. Are we pursuing a reasonable goal? Another thing we want to know, what are the data? If we're going to do this study, we need to know what kind of data we're collecting. It could be a survey with yes or no questions. So that means that, all right, we're going to be getting yes or no as data. It's going to involve getting information from people. And the survey, it could be online. It could be something where we call people randomly. It could be the kind of thing where we're handing out sheets of paper and people are answering questionnaires. This could be numerical data. We could be asking people, say, how many times they've been to Subway in the last month, and we'll get answers like 1, 2, 3, 4, 17. So we want to know what kind of data we're looking for, this will tell us what kind of tools or devices or surveys that we're going to need to put together. It might give us some idea of what kind of random sample what kind of technique we're going to need to use to put together a good sample that's reflective of the population. So there. So identifying the context. Another thing we want to consider is the data source reliable? Say, for example, you're studying lightning strikes, and you're trying to come up with some idea is, well, does lightning strike twice? Does it hit the same place twice? And let's say you have a mountain where there are lightning strikes on this top of the mountain, so they're certainly hitting the top of the mountain more than once, but are they hitting exactly the same place on the mountain more than once? So you have some meters up there, or some kind of device that's able to locate where a lightning strike occurs in a space, say, that's maybe, golly, hundreds, well, let's say 50 yards by 50 yards. So 2,500 square yards. Well, in that case, you could say there's an older device up there. It's been there for a while, maybe 30 years. And, well, you might want to make sure, is the device working properly? It's been up there for a while. It's been working for a while. Machines break down. So we want to make sure, okay, is it still okay? Is it working? Is it not degrading over time? Now, you could have a new machine up there, brand new. And it's like, well, okay, but how do we know it's calibrated correctly? It hasn't been put through the test. It hasn't put through any rigors of use. So maybe there's something off about it. Maybe there's a defect that we don't know about. So you want to be careful about the reliability of our data source and things like that. As far as samples go, bias. Again, this is where the random samples can be really important. Do we have a sample? This is going to be the source of our data, will be the sample. Does it really reflect the population? So again, something we want to think about. How we put together that sample could affect the reliability of our data. All right. And this is more specific here. So I've already mentioned this. Is the sampling method sound? And again, the issue here is it an accurate representation of the data? Again, does this sample really look like a miniaturization of the population? All right. They mentioned something in the text here, and it's kind of an example to kind of be aware of. And I've mentioned bias, but there's other things that can kind of go wrong here. And I'd put this under accuracy of the representation. Oh, I'm sorry, not data, population, I'm sorry. And what can cause this? We talked about like sampling techniques where, you know, you need, if you're going to do a sample, say, of New Mexico, most people are going to be coming from the I-25 corridor. You would want to expect that to be reflected in your sample as well. Another way you can get a sample that's biased volunteer or self-selection bias. What happens here is if you ask, say, a question, you want people to call in, you're asking some question about taxes or something. It turns out that the people who call in might have a very different point of view than people who don't. So the people who are calling in might not represent all the views available for whatever question you have about taxes. And the book speculates that people who don't call in or who don't volunteer to fill out your survey, they might have a reason not for doing that. They might not feel safe doing it. It might be something that they just feel discouraged about. They just don't want to think about it. There's a lot of different things, a lot of different reasons people might not volunteer. In some ways, you could argue that generally people don't volunteer to do surveys. I don't know if that's true or not. And when you do volunteer, sometimes maybe that's because you have a very strong position on this and you're incredibly motivated. You have this very motivated point of view. While the people who aren't volunteering, it's not that they don't feel strongly about it, but they're not motivated because maybe this is the status quo, things are already like this and they're comfortable with it. They just want to leave things are, and that means leaving your survey where it is, which is not in their hands. So who knows? I'm just sort of trying to guess. I'm speculating, not necessarily thinking critically. But it has been observed that when people volunteer themselves to take these, like you just say, hey, who wants to fill out my survey? You aren't necessarily going to get an accurate representation of what everybody thinks. There are people who aren't filling out those surveys of yours, and they might have very different points of view about the topic than the people filling them out. So we call this self-selection bias, where someone volunteers themselves, selects themselves out of the population to become part of your experiment or to fill out your survey. So that's another form of bias that can come in. All right. Wow. So that's the preparation part. So as we continue on in the process of a statistical study, we've looked at the preparation, we want to prepare, and then we're going to analyze. So one way we could do this, again, graphs. Great way to look for patterns. Great way to see if most of your results are centering on some number. We might explore things numerically. So again, this could be, well, outliers, look for outliers. Unusually large, unusually small values. When we graph our values, we see some value that's way out there. Look for outliers, and then sometimes you can't always tell why an outlier is there. Sometimes it could be something as simple as the person who was writing down the number accidentally wrote down the wrong number. Instead of writing a 3, they wrote an 8. There's just handwriting, and they're doing this at 4 a.m. So who knows? Let's see. We might summarize data. And we saw this earlier. And again, things like the average or the mean, the standard deviation, say the mode, talking about how frequent different values, numerical values come up. All right. We might look at distributions. Here again, we look at how spread out the data is. And we also look at, if you have repeated data values, where those repeats are happening. Are you getting a lot of repeats around the number 0? You're getting a lot of repeats sort of at -53, a lot of repeats at 53. So we'll look at how the data is distributed and where you get repeated values or where a lot of values seem to be coming together. We'll also look at missing data, something to keep in mind also. And then something else they mentioned too. Response refusals. They have this under explore numerically, but it did come up in the discussion in the text that this is something we also want to consider. The thing with response refusals is it's not that someone necessarily, well, you can think of it as kind of a volunteer bias where you have someone who refuses to volunteer. And there's various reasons why people refuse to respond. They could be too busy, for example. Let's say you're asking a question about how do you feel about the outcome for this particular football team in this particular game. And let's say in that particular game, there was a heart-crushing bad call by the referee. And if it wasn't for that call, that particular team would have won the game. And it turns out you called up the person who's a huge lifelong fan of that particular team, and they just don't know. I don't want to go there. No way. I'm hanging up. Sorry. Have a good day. Sometimes, who knows? So response refusals, well, there you go. And again, just like with the person who doesn't volunteer, there could be points of view here that aren't being represented, but clearly if they're refusing to respond, how do you get that point of view? That's going to be hard. So that's something we're going to have to consider when you do your statistical study, especially when you make conclusions. Just because someone refuses to respond, that doesn't mean they don't have a valuable point of view. See why this subject can get really tricky. All right. So trying to find out that point of view, that could be very difficult. All right. So again, that's why this subject could be very tricky. All right. So prepare, analyze, and then we're going to apply the third and final step of our process, statistical methods. I mentioned earlier that there's really kind of two definitions for statistics. The one that we have is the science of planning these kinds of experiments or these statistical studies. And the idea is that there's a second definition too. And the second definition is a statistic as just a noun. Well, statistics is a noun also, but very specifically, a statistic can refer to a function. Remember functions, remember f of x. It's still with us. These are functions that take data as input, and they'll output some kind of number, or they'll output some set of numbers. So they'll take in our data and say, an example of a statistic, it'll take in sample data and it will give you an average. So sometimes we'll refer to a statistic as that kind of a function. So like the mean function, statistical mean, that will be a statistical function. These are going to be mathematical methods, mathematical tools. And it's often done with computers. Now, I'm going to show you later some free piece of software. It's actually a programming language called R that lets you do this. You can download it, it's free, and you can compute all kinds of things: means, medians, standard deviation, variances, correlations, correlation coefficients, these kinds of things. We'll talk about what those are later. And the reason we're going to want to use computers, some of the calculations are kind of rough, especially correlation coefficients. So we're going to have a computer do that because some of the calculations are, kind of difficult. They're involved. Even ones that we can learn how to do, or we can learn how to do correlation coefficients anyway, but I don't know if we want to. Well, we'll get to that bridge. We'll think about it. It'll be fun to show you how to do it. So it's going to be a lot of work, though, especially if you have huge data sets. Huge data sets. It's one thing to try to compute a correlation coefficient at least once, just so you've at least done it, with maybe 10 pieces of data. It's a different thing to compute it with 1,000. To do that by hand, you could be there for a while. So in statistics, since we're working with huge sets of numbers, huge sets of data sometimes, we're going to just let computers do this. We're going to find a way to get the data into the computer and let the computer compute the mean, so we don't do it by hand. Let it compute the standard deviation. We're not doing that by hand. Let it do the correlation coefficient. We probably don't want to do that by hand. So we're going to use computers to do our to apply statistical methods. All right. And let's see here. Oops, got ahead of myself. There's one more stage. So we prepare, we analyze, we apply statistical methods. That's under analyze. So for the apply statistical methods, I want to indent that one. It's part of the analyze section. The true third and final is to conclude. And we're going to look for things like statistical significance. Is it there? We're going to talk about what this is. In a nutshell, what it's saying is that when we do our study, we kind of have this assumption that we could get results that are just random. We're doing a random sample, and so there's going to be always some kind of a bias, or there's going to be some of those things that just kind of happen. Sometimes there's a slight trend to this direction, and sometimes a trend to that direction. But there's sort of acceptable fluctuations, like if you compute, say, the average opinion of Subway sandwiches, rating it from 1 to 10. So they're talking about some specific sandwich. And you might find that in one sample, you get an average of 7. In another sample, it's 6.5. In another sample, it's 7.25. In another sample, it's, say, 6.79. In another sample, it's 7.05. But you kind of see what's going on here. We're kind of, no matter what samples we do, we're typically kind of falling in between like 6.5 and 7.5. We're not getting the same average for each sample. Sample of 500 here, sample of 500 here, sample of 500 here. Each one will have a slightly different average, and we kind of expect that. You're going to have that. It's not going to be perfect. So there's going to be some random variance between the averages for each sample. And so we might say, well, that's not statistically significant. Again, the sample is a very, very precise and hopefully very accurate guess about what the population truly thinks. So based on these little samples or miniatures of the population, there's going to be some variance. And so we expect that. When something's statistically significant, we're going to get a result that's very different. it's not going to be like something close to 7. We might get some average, it's like 8.9 or something. And we have to, oh my, we have to kind of consider what's happened. Like say in the past, the average opinion rating this sandwich from 1 to 10 was like about 7. And so 2 years later, it's been fairly consistent that way. And then 2 years later, we do a study, we find out, no, it's gone up to 8.9. And we have to ask, is that a statistically significant change? If we had gotten 6.9, it's like, well, that's not really different from what we got before. So that's probably not statistically significant. But if it's 8.9, well, that might be statistically significant. So this tells us if the result that we get isn't really small, does it really indicate something new is going on or something is different from our previous expectations. So for example, if you're trying to work with, say, does a drug work? They'd say prevented virus, like we talked about before. We might have some expectations about the drug, and then, well, we do our study and we get something that's very different. You know, is it different enough, or is it kind of fall within the range of what we expected or what we've seen in the past? So the question of statistical significance, we have to answer that question. All right. There's another thing called practical significance. So with practical significance, just becomes just something statistically significant doesn't mean it's practically so. Another way you could think about this, let's say you're putting in tiles on a floor. And you've seen those tiles where they're really close together and it's just like the floor is perfectly flat, or maybe it's a countertop and it's just perfectly flat. And you have some sort of device, some sort of laser-based measurer that can measure the almost imperceptible heights between tiles that are next to each other. And you're trying to figure out, okay, well, what are the differences in microscopic differences, it seems like, between the heights of next or adjacent tiles. And you might find a tile, let's say it's, gosh, on average, you find maybe it's 1/10 of a millimeter, 1/15 of a millimeter, 1/10 of a millimeter, 1/12 of a millimeter. You're just finding these fractions of a millimeter. They're like 1/10, 1/12, 1/15. Or let's say, maybe that's not the best way to put it. I'm sorry, let me go back. Say it's, 1/10, maybe it's 2/10, 1/10, 2/10, 1/10. And then you find a pair of tiles that's 2.9, it's 3/10. It's like, well, they're either 1 or 2/10, but here's this one that's 3. And you might say, well, all right, they tend to be 1 to 2/10. 1 to 2/10 of a millimeter. Would one that's 3 out of 10, 3/10 of a millimeter difference in height, 1 2/10, 3/10 of a difference, maybe 4/10 of a difference. And okay, 4/10 might be significant. If they're usually 1 or 2/10, but then 4/10, okay, that might be a significant difference. But here's the thing, this countertop, you don't really use it for anything other than just putting plates on it or something. And granted, it's statistically significant, it might be. But is it practically significant? I mean, does it really matter if the difference between the tiles is 4/10 of a millimeter? So it might not matter. So even though you might have statistical significance, the tiles are usually 1/10 or 2/10 of a millimeter. A millimeter's like tiny. 4/10 might not make a difference. Heck, depending on what you use of the calendar, a full millimeter off might not be a difference. This isn't actually a millimeter. Millimeter would be like something really tiny. So just because there's statistical significance doesn't mean there's practical significance. So anyway. So there's some pitfalls in statistics, things we want to kind of keep an eye out for. And we've talked about a lot of that throughout the lecture. Okay, I kind of rambled about a lot of that throughout the lecture. Let's look at pitfalls specifically. So we want to be careful of this. Misleading conclusions. So specifically, don't make statements unjustified by the statistical analysis. And this, again, you could think about what we talked about with statistical significance versus practical significance. Yes, this countertop might have these two tiles that are 0.4 of a millimeter difference in height. And all the other tiles overwhelmingly are 1/10 of a difference in height or 2/10 of a difference in height. But there's these two that border each other and the difference in height is 0.4. Okay, fair enough. But if you make some claim, therefore, that makes the entire housing structure unstable. Well, you got to take a look at, is that true? You need to take a look at where these tiles are located, and is that actually going to be significant practically? So, or you can make some claim that clearly such a damaged or not consistent countertop would not be fit to use to bake a cake. Again, is that really supported? You don't want to make misleading statements, because when you say something statistically significant, significance, what stands out in our minds, significance, this is meaningful, we need to respond to it. Well, practically, we might not need to. So we want to be careful with this. All right. Another one, this is a famous one. Correlation does not equal causation. So again, this is like that virus example I talked about earlier. I kind of changed it as I went through. So let's say we're trying to come up with some kind of drug that prevents you from getting some kind of virus. And say we're in the middle of the, or we're going to launch this sort of towards the end of the virus season, and unawares perhaps. And we notice that as time passes, sure enough, people aren't getting sick anymore, and we've been giving a random sample this new drug that prevents you from getting this virus. Unbeknownst to us, it just so happens, say this is like a very, very new virus that we don't have any information on. So we don't know sort of the season when this virus becomes, well, very rampant. Like you have like the cold season and the flu season. So we might say that, oh, look, the number of people getting the virus is dropping as we give everybody our preventative medicine. And since we don't know, we didn't realize that, well, this happens to be the end of this virus's season. Again, this is some new virus that we don't know anything about. We might make the dangerous conclusion that it's our drug that's doing this, not that the seasonal change is causing the virus to go away. So another example, and this is a silly one, is let's say you decide you want to test whether or not eating, let's say, chocolate in the fall causes birds to go away. And you do a study on this. Does the consumption of chocolate by the population cause birds to leave? I'm going to say we're living in the northern hemisphere, and where we are. And I just want to be careful. Birds, hemispheres, All right, not an ornithologist, so I want to be careful here. I better just stick to math, but I'll stick with this example. Say we're in New Mexico. Does eating chocolate in the fall cause birds to go away? And you, sure enough, you hand out, you get a sample, and you say, all right, your duty to science is thus. You need to eat chocolate. And they're like, I'll do my best. So you give them chocolate. Some people may get sugarless chocolate, and we're eating chocolate. And what's happening is that as we're consuming this, sure enough, we're going to notice over the next 3 months, it's a lot of chocolate. It's kind of a fun experiment. And the birds are gone. It's like, oh my gosh, it worked. To make birds go away, eat chocolate. And so we write up some paper that says, look, we've heard there are regions in the world where birds will flock into, say, farmers' fields, devour seeds and crops and things like this, and then go away. We've got the solution. According to our study, we found out that if you feed the community chocolate, the birds will just go away. There you go. Well, this is the difference between correlation and causation. Oftentimes things can happen at the same time. Call it coincidence. It doesn't mean one thing is actually causing the other. So you want to be careful. Just because we see things seemingly reacting to each other at the same time, that doesn't mean they're actually affecting each other at all. There could be something else that's causing the birds to go away in the fall. It's nothing to do with us eating chocolate. So a big one, correlation, where we see things going along, and we'll do studies. We'll find very strong correlation that as we're, say, eating chocolate regularly throughout the fall, the birds are just, the populations are thinning out and gone. That's going to be solid. Doesn't mean the eating of chocolate's causing that to happen. Something else could be doing that. And we're seeing some kind of a parallel, a coincidence. All right. Similarly, patterns. Do not equal relationship. And this is another sort of correlation does not equal causation. It's similar to that. Excuse me. So again, when we deal with this, and this is different from like science, it's different from algebra. In algebra, you get an input, you put an input into a formula and you get an output. And the choice of input affects the output. Here, we could see something that looks like that's what's going on, but it actually isn't. There's no connection. There's no formula between the two. So again, that's what could be kind of tricky with statistics. So it really looks like there's a cause and effect relationship. No, it's actually just coincidence or parallel behavior, but not cause and effect behavior. All right. Another thing, we're still looking at pitfalls here. Reported versus measured data. The issue here is measurement. We're using some sort of standard of measure. So let's say we're measuring temperature. So we're going to go around and ask everybody in town, what's the temperature? Well, again, that's the population. We're not going to be able to get to everybody. So we come up with a sample, say a sample of 100 people. And we say, okay, I'm going to give each person a thermometer. And again, this is part of the preparation. I mean, there could be some bias in the thermometers. They might not function quite the same. Little differences in the manufacture of the thermometers. But hopefully, we'll have to make a note of that. And hopefully, we can do some kind of study before we give our random sample thermometers. We can actually take a look at these thermometers and see, well, how much variance is there between them in the temperature range that we're going to be studying. Now, they could get more variance when it's really cold or more variance when it's really hot, but in the range that we're looking at, hopefully all the thermometers are behaving and measuring roughly, very, very much, not roughly the same, very much the same. All right, so we're going to hand each person in our random sample a thermometer. So this is going to be measuring data. They're going to measure the data. They're going to stand outside in their particular part of town. Okay, the temperature is, and we're going to try to come up with some average temperature for Roswell. All right. So measured data. Now, even that's kind of like reported data because they might hold the thermometer slightly different from each other, and that's going to be the issue. If we ask people to go outside and just tell us what they think the temperature is, without using some kind of measuring device, we could get a lot of different answers. Some people might say in July that it was pretty hot last week, it feels cooler now, and maybe it's 85 degrees. And then someone else who during that hot streak was in air-conditioned office the whole time, air-conditioned car, air-conditioned house, really well air-conditioned. And they actually have to spend some time outside today, and they're like, this is so hot and miserable, it's got to be 110. And then you'll get people say, it's probably 98. Someone else say, it's 104. You could get all kinds of answers because reporting can be very subjective. And so reported data versus measured data, we're hoping we have some standard of measure that's going to help, again, try to get a more accurate picture of what the temperature is in Roswell. And reported data, we might not get that. And again, even with the example I gave, if you're giving everyone a thermometer, well, they might accidentally put a finger on the thermometer, that affects the temperature. There's going to be some issues here that you get with reported data also, because human beings, in the end, we are reporting the data, and we have all kinds of little biases and slip-ups that we do. So that's going to be one of those things we're going to have to keep an eye on. All right. All right. Loaded question. How we ask a question can influence the response. And this is something that, well, give you an example. How do you like those awful hot dogs from some restaurant in town? If you ask that kind of question, what kind of responses do you think you get? And that's clearly a loaded question. Now, it's funny what kind of responses. You can get people who think, oh, these are awful. Well, maybe I didn't enjoy those hot dogs as well as I thought I did. Well, they were okay. Or someone who really liked them, like it's the best hot dog they've ever had. Well, okay, best one they've ever had. And then you ask them how you like these awful hot dogs. They're like, these are amazing. And then, they'll give you that. Or it's the best hot dog they ever had. And they, well, maybe not the best. Let's say it was just good, but it was, they liked it and they got offended by you calling them awful. And then they might say, well, it's the best hot dog I ever had. Loaded questions can really alter your results. Now, there's an example of a interesting type of questions issue. And this is the order of questions. Ordering. So for example, and they mention this in the text, I can't remember off the top of my head the two products or companies they were comparing, but it'd be sort of like asking, which do you prefer, Ford or Mercedes? Or what car would you prefer to have, a Ford or a Mercedes? And, new car, brand new car, and there's different arguments for either one. And you're going to get it for free. And what they found is that if you say Ford or Mercedes, you're going to get a different response to that question, or you could, if instead of asking Mercedes or Ford. So the ordering in your questions can also influence the response. That's another pitfall to keep in mind. And of course, non-response. We mentioned this earlier. It does not mean they don't have an important point of view. It may be tempting to dismiss non-responses as just kind of white noise that you get in any kind of experiment, but this actually isn't necessarily the case. Again, people might not respond for very important reasons, like they might not feel safe they should respond, they might be complacent about responding, or they don't want to relive that football game. They just want to let it go. So the non-response could still be very relevant, the point of view that it has. All right. Now the last thing to mention, in this we get to do some numerical stuff, and this is going to be a bit of a review. It's percents. So we talk about percents. We're going to be doing this a lot in this class. When we talk about statistical significance, when we talk about, normal distributions, we'll be getting into percents. And the idea is this. A percent just means a denominator of 100. And that's it. So 6% is 6 over 100. 1,000% is 1,000 over 100. That's it. Let's say you have 0.03%. Well, that's 0.03 over 100. Yes, we'll even give a decimal number a denominator. So that's what percent means. All right. So for example, if we want, let's say, 5% of 200, of in this case is going to mean multiply. So we really mean 5%, and this will be an example, 5% times, I'm going to use the dot for times here, 200. And you might be saying, oh, that's 5 times 200. It isn't. Remember, 5% means we need to put a denominator of 100. We need to convert the percent to the fraction. Multiply these together, and what you'll get, you can use a calculator here. Take, say, 5 divided by 100, put that in parentheses, and your calculator would look like this. And then use that little asterisk symbol, Shift 8, usually on a keyboard. Or just multiply if you're using your calculator. Type that in, and what you'll get is 10. 5% of 200 is going to be 10. All right. So, things that you're going to want to know how to do with percents. Well, first off, percent to fraction. Well, we've seen this already. If I have 6%, well, that means it's 6 over 100. Just give that the denominator of 100. Okay, we got to reduce it. Since we are going to fractions, we got to reduce. So how to reduce 6 over 100? Let's think about this. To reduce, we can divide the top and the bottom by the same number. And what I mean by divide, that means you don't get a remainder in this case. So there's some number that 6 is divisible by and that 100 is also divisible by. Well, they're both even numbers, so I bet it's going to at least be 2. 2 will always divide into an even number without a remainder. So if we divide top and bottom by 2, we always divide the top and the bottom by the same number when we're reducing fractions. We'll get 3 over 50. And some reflection is going to tell us that, well, there's no number that 3 is divisible by, that 50 is also divisible by. Don't have a number like this for this. So this is as far as we can go. So it turns out, when all is said and done, 6% is 3/50. Learn something new every day. It's kind of neat how these percents will have a very different look when you make them in the fractions. Let me show you another one. Ooh, getting complicated here, 0.4%. Well, no, we do what we did before. Give it a denominator of 100. 0.4 over 100. How do you reduce that? I mean, even number here, even number here. Gosh, seems like we should be able to reduce it, but the thing is we want to make this a fraction, and we know with working from fractions, they don't have decimals in their numerators or in their denominators. There's a decimal here in the numerator. We want to get rid of that decimal. The way to do that, we need to move it over here. The only way we can do that is you have to multiply this by 10. Remember, every time you multiply by 10, you move the decimal one spot to the right. There's a rule with this. When we multiply the top of a fraction by a number, we have to multiply the bottom by the same number. It's also true of division. If you divide the top by some number, you have to divide the bottom by the same number. So when we do this, we're only changing the form of the fraction. The quantity means the same thing. It's like 1/2 versus 5/10. 1 is half of 2 and 5 is half of 10. They both represent this quantity of a half. So they're just different forms of the same thing. So what we're going to do, multiply top by 10, multiply bottom by 10. Multiplying a decimal number by 10, we'll move the decimal over one spot. We'll get 4 over 1,000. Now we can try to reduce, and it turns out you can divide top and bottom by 4. No remainder, no remainder. Both are divisible by 4. And so we'll get 1 over 250. There you go. All right. Now, we might want to do something else, though. We might want to go the other way. Now, to do this, we got to do something first. We need to talk about decimals and percents. We'll come back to this. So first off, go percent to decimal. How do we do this? Well, what we do is take our 6% and we can turn it again into that fraction. A percent is always a fraction with a denominator of 100. Now remember though, fractions, there's another meaning for them. Usually it means a part over a whole or part out of a whole. Like if you have a pizza that's 4 slices and you eat 3 of them, that means you ate 3/4 of the pizza. So of the 4 pieces, you ate 3 of them. But another way you can think of a fraction is this. A fraction is division. So we rewrite the percent as a fraction, and it's always going to be over 100. And so we divide by 100, we're going to get this. In general, if you want to skip this step, you can always take the number here and divide it by 100. That will give you the decimal representation of that percent. So if you have, for example, 200%, just take 200, and you always divide by 100, and you get 2. The decimal equivalent of 200% is 2. At 70%, just take 70, divide by 100, you get 0.7. So a little faster way of doing it. So now we want to go the opposite direction. And we haven't forgotten about this. Decimal, 2%. So what we did before, we took our percent, we divided by 100, and we got our decimal. So now we want to go backwards. We want to reverse this process. So we're going to take a decimal, and to reverse the process, we've got to do the opposite of what we did before. So instead of dividing by 100, we multiply by 100. And again, I'm using the dot for multiplication. And that gives us the percent. Since dividing gave us a decimal, we're going to do the opposite of dividing. We're going to multiply to get back our percent. All right. So if we have a decimal, say 0.03, we take 0.03, multiply by 100, and you get 3%. And there you go. Well, let's say you have the number 42. What's 42 as a percent? Well, this is a decimal number. It's 42.0. So we take 42 times 100. And when we times 100, it's actually technically, you could argue you're multiplying by 100%. But when we multiply by 100, the answer is always going to be a percent. Get 4,200%. Yikes. There you go. So this here is going to let us answer that. All right. So going back to this, I'll give you a second to maybe write this down in your notes again. Fraction to percent. What we're going to do is this. We're going to go fraction to decimal, and then decimal to percent. So let's say we have this, 1/4. So again, 1/4, that's the same as 1 divided by 4. Put that into your calculator, or you can do this using long division, but you'll get 0.25. So that's our first step, fraction to decimal. Then we take our decimal, multiply by 100, and when we multiply by 100, we're going to get a percent as an answer. 0.25 times 100 is 25, and this is going to be 25%. And there you go. Do another one. Get 1/3. Well, 1/3 is 1 divided by 3, which is 0.333. Okay, it just repeats infinitely. But then if you take this number, multiply by 100, you'll get this. Don't forget, it's a percent. And there you go. You can convert fractions to percents. Now I want to show you kind of a tricky one. You might encounter this at some point. Let's convert this to, say, a fraction. So this is what's called a mixed number. And with a lot of these kinds of calculations, it can help to convert the mixed number to an improper fraction. So if you recall, with a mixed number, you have a whole number, a numerator, and a denominator. To turn it into an improper fraction, you keep that denominator, multiply the whole number in the denominator, and add the numerator. That's the formula you're going to use. So that means, and let's say this is, make this a little different. We'll call it 1/4. Keep the denominator, whole number times denominator, plus numerator. So this will be 8 plus 1 over 4, or 9/4. So we're going to convert this, and this is percent. Remember, this was 2 1/4%. So it's going to stay that way. Get my percent signs in there. Now we want to turn it into a fraction. This is a percent. Now it's a fraction percent, but we want to be careful. We just want a fraction with no percent. So remember, every percent has a denominator of 100. Now what that means here for this fraction is the entire fraction gets a denominator over 100. Whatever the object that's the percent, the whole object's on top, the 100 goes underneath the whole thing. And this is going to be divided by 100. Now, we can use our knowledge of dividing fractions. Remember KFC. Keep the first fraction. We're going to flip the second one, and we'll change the C. We'll change division to multiplication. KFC. Now, this 100 here doesn't look like a fraction, does it? But you can rewrite it as over 1. Any whole number, any natural number, any integer, you can turn it into a fraction by giving it a denominator of 1. Because 100 divided by 1 is still 100. We haven't changed the quantity, we just make it look different to help us work with fractions. 100 over 1 is the same quantity as just 100. So we do KFC. When we multiply fractions, we multiply across. Get 9 over 400. Wow. So 2 1/4% is 9 over 100, over 400 is a fraction. So there you go. That's our first section. And if any questions, let me know. Other than that, have a wonderful evening.